So now let's get into actually using the formula for volume. So again, when we're doing volume, we're doing the area of the base times the height. So pi r squared is the area of the base. Now we need to multiply by the height. So when we're doing this, notice how this is in terms of pi. So we don't actually have to multiply pi in our calculators. So when we're doing this, go to your calculator. Let me pull one out. And our radius is 6. So we're doing 6 squared. So 6 times 6. And then we're going to multiply that by the height, which is 13. So it's going to be 468 times pi. 468 times pi. So sometimes you have to read the question if it says in terms of pi or not. And this can be crucial because sometimes they'll already have the pi written out. So just be careful. This one, obviously, all of them were in terms of pi, so it was really obvious. Oh, let me delete this. So look at the next one. What is the height of the cylinder in the diagram? So they give us the volume. So we're going to use our formula. V equals pi r squared times height. If our volume is 904.78 equals pi r squared times height. What we're going to do here is we're going to divide both sides. Well, 6 times 6 we already know is 36. So we're going to divide the 904.78. We're going to divide that by parentheses. Make sure you put parentheses. The reason why you want to make sure you put parentheses is you want to make sure that you multiply the 36 and the pi before you divide out. Otherwise, what will happen is it'll divide the 36 and then multiply by pi, and you'll be at a much bigger number. However, I'm going to use Desmos, which you'll see shows me how it's going to divide it out. But it is important to use those parentheses otherwise. So we're going to do 904.78? Yep, 904.78. Use the division sign, and you can see that I can see what's on top. So, and what's clearly on the bottom, making this easier so I don't have to worry about parentheses as much. So when I do this, I get a clear 8. Yeah, there's more spots here, but that's just because pi goes on forever. So there's no way to get a perfect number, but I'd say like 4 decimal places is pretty accurate. So I'm just going to say 8 here. Perfect. And as always, I'll give you an explanation on how to do it. Moving on to the next slide. So now we're going to deal with cones. So as I mentioned with cones, it's essentially the same thing as a cylinder. We're just going to divide by 3. And in fact, this activity actually has us comparing them at some point. Or I thought they did. So here we're going to manipulate the height. So first we're going to have to open up this other page. And we see the cone. All right, and they gave us a number here. And this time, I really hate how whoever wrote these leaves it in terms of pi, but the calculator doesn't. That feels a little dumb. So what we're going to do here is just do all of them, all of these, and just kind of get an idea for it. So 12 and 14, so the radius is 12, the height is 14, and then we need to figure out the area of this, and that's going to be 2000 So 2111.2. We're going to move on to another one. We just have to technically just only move one aspect of it. So I'm just going to move this to 10 just because the other one did have 10. So doing this will give us a little similarity to this. Just the height's going to be different. So we're going to say 10 and 14. Honestly, there's no purpose. I'm just kind of doing this. 1466. 1466.1. And then you guys, I'm sure, can figure out how to do the last one. Let's just move on. I don't want to make this a three-parter. While keeping the height at a constant vertex, so not directly above the center of the base, check and allow oblique freeze height to assist you. Does changing the position of the vertex change the volume? Okay, so what we're gonna do here is they want us to move this over without changing the height itself. So let's see how they describe the oblique cone. Okay, so this cone can move sideways, side to side. The only problem that I have with this is it doesn't lock the height into place. And there's no options. The last one, there was other ones that had options, but this one apparently does not. In fact, this one doesn't. Um, I'm not really quite sure how we're supposed to figure that out using this. Um, yeah, this is weird. Okay, because this doesn't calculate our volume. So, volume of a cone. Okay. It only lets us change the height when we're doing that. Let's see if I can. Okay, freeze height. Oh, okay, there we go. Freeze height allow opaque. So this was in the original one. I don't know why they gave us one otherwise. So I'm going to freeze the height, and I do this, and you see that even as I move it, the volume stays the same as long as the height stays the same. And you can kind of see why, because this is stretching out, and actually it's not really necessarily stretching so much as a lot of the cone space is going towards moving this way. So the volume does stay the same. So think of a cone stack and disk. We'll actually talk about this later. Um, but what's happening here is, so the cone, the cone's volume remains the same even if the tip of the cone is not directly above the center as long as the height is constant. So what I'm basically saying is as long as the height stays the same, even if it's not above the center, the volume's still going to stay the same. Um, and this is saying like think of a stack of discs, and I feel they're introducing this a little early, or actually no, we talked about this when we did volume. This is because of Cavalari's principle. So this is because of the Cavalier's principle. And if you guys need a refresher on Cavalier's principle, what it was it was a stack of discs. And if you move those discs or coins, I think coins made more sense. If you move the coins, you still have the same number of coins, which means you still have the same volume. The shape's just kind of a little different. So that's the idea here, is now we're going to have coins that keep getting smaller and smaller and smaller. We're just kind of pushing them over. So it looks like it's getting skinnier, but what's happening is it's just getting pushed over. All right. Using your algebra skills, rearrange the formula to find the radius when the height and the volume. So we're gonna do another algebra problem here. I honestly don't find these that challenging compared to some of the abstract concepts they give you. So what you're gonna want to do here is write the original formula. I say go to equation editor. It just makes your life so much easier. So we're going to do this. We're going to do volume equals the fraction of pi r, push the exponent button, square times height, all over 3. This used to be how Google did it before they stopped giving the formula. I'm assuming they're doing it to prevent people from looking it up, but it still comes up there with Google Images. So we have this, and we want R to be the same. So the first thing we're going to want to do is we're going to want to multiply that 3 to both sides. 3v equals pi r squared times height. Where is this? Pi r, and this should remind you of the formula for a cylinder. So as you can see, a cylinder would be 3 times more than that of a cone with the same height and radius. Then we're going to have to divide out the pi and the height. So this becomes, now the fractions on this side, 3v pi, where's my pi? H, and this is equal to r, control up, squared. And then we want to find just r by itself. So we're going to say r equals, the way we got rid of the squared was by square rooting. Going to have a fraction in there, 3v pi h. And that's how we solve for radius, given the height and the volume. All right, so how did we do? I'm gonna give myself a 4. It was a little difficult finding the oblique option, but once I found it, the problem was easy to solve. All right, and we're about halfway done with this module. Well, with this tutorial, to be more accurate. All right, so moving on here, now we need to find the volume of this diagram. Now, remember, our formula is volume equals pi r squared h divided by 3. This is an r, not a diameter. They're giving us a diameter, so we're going to have to divide this by 2 to get the actual radius. So we get pi 5 squared 18 over 3. Well, 18 divided by 3 is 6, so this becomes pi 25 times 6. So I did the squared and the divided by 3 at the same time. And this ends up being, I have 6 quarters. So if I think of 6 quarters, I have like $1.50. So it's going to end up being 150 pi. So by quarters, I mean the value of 25. All right. So let me erase all this and we'll get to the next slide. Oops, need to go back to mouse mode. All right, so what is the radius of the cone in the diagram? Round your answer to the nearest whole number. All right, so again, we're gonna have to do this. This 201.06 is equal to, so it's V equals pi r squared h over 3. We could actually use the formula that they gave us before. So I think that's the reason why in the activity they make you solve for another formula. But I'm just going to plug it in here and then just use algebra to figure it out. R squared, h is 12. So what I'm going to do is I'm going to divide this whole thing by 12 pi, and then I'm going to square root that. So this is going to end up being 201.06. 12 pi equals r. I'm going to get rid of that by square rooting. And then I can just plug this into Desmos. So remember desmos.com, go to Math Tools Scientific Calculator. I'm going to delete this. And what was might as well close this one. 201.6, 201.0. Was it 06 or 6? Yeah, 06. We're going to divide this by 12 pi, and I almost forgot the square root part. Oh no. I'm going to square root this. So if you actually type in SQRT, it actually does do the square root. The only problem is I should have done that first. All right, and they want the nearest whole number, so the answer is 4. The reason why they do that is just in case you're not using a calculator. Oops, I forgot to put the pi here. Just in case you're not using a calculator, that pi might make things a little bit difficult. Um, huh. This is interesting. Oh, derp. I got lucky because of the fact that I forgot to divide by 3. So that would have made this 4. Because 12 divided by 3 is 4. So I kind of got a little lucky in that regard. Because this should be 4 pi, which makes it 4. So I got a little lucky there. I didn't realize that I didn't bring down that 3. That would reduce it. And I also got lucky because on top of not getting that 3 pi. So pi and 3 are kind of similar because it's 3.14. So that's why my answer was really close, but I did make a couple mistakes there. All right, so going on to the next one. Let me erase this. The next one we're dealing with is pyramid. So if we remember pyramid, it's essentially the third of it. So because it's a triangle, it's kind of like a cone is a type of triangle. We're going to do the base. So the area of the base, sometimes it could be side squared because it's a square, or sometimes it could be length times width times height divided by 3. That's our formula for a pyramid. However, like if a pyramid has a different shape at the bottom, then we have to use a different formula. So let's get into this one. All right, so now we're just going to do a square pyramid. So what we can do is we go to this activity here, click on the volume of a pyramid. Let me close, well, I might need that calculator later. So I'm going to do a square pyramid. So this is 10, 10, and 7. So base length, so it's a square, so it's going to be that 10. This is going to be 7, and our height, so you can see here, it's L squared instead of LW. Our area is 233.33. 233.33. I'm sure from here you can do the rest. I'm not going to go through all of it. You guys should be able to pick out your own examples. Now we're going to try it with a rectangular base, meaning that we want to drag this, but here's the problem. It's a square base, so I think there's another one. Where is it? Area of a regular polygon? No, although that is useful in case it's a different shape. We want this to be Let me see if I can make it a rectangle. Keep base square. Okay, there we go. So you have to undo keep base squared, and then you can move this to have a different length and width. And that you're going to do the same thing, except instead of it only being one base length, you're going to have a length and a width and a height. So again, you have to complete all of these. So just put them in, write down what the volume is, and continue from there. So this next one we're going to do is we're going to do a rectangle and a square pyramid. So the difference between the two, what values of length of four sides value produce the identical value. Okay, so suppose we want to design a set of four congruent square pyramids. Combined volume is the same of a single rectangular pyramid. How many values of each square pyramid? So I'm not quite sure what they want us to do here. The main idea is if we're gonna do a square pyramid, we're gonna have to try to match all these up. So for example, one of them is squared and height. So what we're gonna have to do here is we have to make LW, we have to make the product of this equal the product of that. Both of them are getting divided by 3, so we can't really do much there. But let's say we had something like 3 squared and, I don't know, 5. This means our product is 45. So in order to make this the same, we would have to have the products be the same. And you guys can do this with any numbers you guys want. So I'll leave that up to you. You can just mess around with this. I would remember, if you're doing the square, you have to go back to keep the base a square. All right, so again, this is up to you. You can do whichever values you want. And like it says, there's more than one answer. The tricky part here is they want 4 congruent pyramids here. So one thing I would recommend is having the product of L times W times H be 4 times more than L squared H. And an easy way to do that is honestly to just make the W 4 times more than the length. That's probably the easiest tip. I don't understand what we're supposed to learn from this, but just for a quick example, like let's say I had 4 squared H, or 4 squared 2 over 3. I can easily just make this 4 times 16 because that's squared. 2, boom, this is going to be 4 times more than that. It's one of the easiest ways, I think, to do it. Make sure you put your volume and times your volume by 4 to make sure it's equal to that. I just find this really weird. Not sure what the purpose is there. Consider the volume of a rectangular pyramid whose base is not a square. Does changing the 3 variables length, width, height by a factor have a greater effect on the volume than changing either the other 2 variables? So this is saying, like, is changing the length more than changing the width, or is changing the width more than changing the height? Is there any one of these that has a greater effect? So let's say I made this 5 times more. The answer is no, because they're all on the same level. None of them have a larger influence. They actually use the word here than the other. So it's like, no, the length width, and height all have the same amount of influence over the volume. And that's because we're not squaring anything, we're not doing anything special to anything. So they all have the same number of influence. Assume that the other two variables remain constant. Explain your answer. So by explaining my answer is none of the values are being affected any differently than the other. For example, and I'm saying this to everyone, for example, in a cylinder, the radius was squared. So the radius was squared in a cylinder, so it had more influence over the volume. Right, and then this, honestly, I would hope a lot of you guys are fives. If you guys aren't fives, it's important to reflect off of that. Don't just put yourself a five just because I said I hope a lot of you guys are. I'm just hoping that I explained it enough. If you guys aren't, like I said, feel free to leave a comment um, on the video so we can open it for discussion. I'm going to say five. It was mainly a matter of plugging in numbers. All right, let's go into the height and base of dimensions of the pyramid. So here's the thing here. This is a different type of base. So we have to find the area of the base. So before I was saying it was always length times width times height divided by 3. That's not necessarily true. This length and width represents the area of the base. So in reality, it's supposed to be area sub base, area of the base, times height divided by 3. So if I'm finding a triangle, I need to find the area of a triangle, which is 1/2 a smaller base. By base, this time I'm meaning the base of the triangle, not the base of the 3D object. Base times the height of the triangle, so it's a different height. So in other words, I get 1/2 5 times 4. 5 times 4 is 20, but cut that in half, that's 10. So I'm going to do 10 times my height, which is 12, divided by 3. You can do this in any order because multiplication and division are in the same area of PEMDAS because multiplication is a type of, or division is a type of multiplication. So it's like I'm multiplying by 1/3. So I'm going to divide by 3, so that's 4. So I get 10 times 4. So my answer ends up being 40. And by cubic units, it means like, oh, if you're doing it in feet, meters, whatever unit you have. All right, spheres. So the formula for a sphere is, I just have this memorized. It's 4/3 pi r cubed. You can have these formulas written down somewhere if you'd like. As always, I always recommend looking at the guided notes. This usually has the formulas somewhere in it. If it doesn't, oh, yes, it has it right here, actually. You might have to fill them out on your own. So I recommend keeping these handy when you're taking your mastery tests. All right, so moving on to the next one. All right, so here, all we're gonna do is just mess around with these. So I'm not gonna go into this. You guys should be able to do this on your own at this point. Change your radius, write down the volume. This one is actually only affected by radius, so that's actually really easy for you to do. Moving on to the next one. If the radius of a sphere is half, is if it's cut in half, use your algebra skills to find the volume replaced with v prime. So in this case, we're going to say that we're going to cut our radius in half. So we have this v prime is equal to, where's the formula? So it's going to be, there's a fraction, 4/3. And you can actually keep everything on top here with the 4/3 pi r, and we're going to control up to make the cube. However, we want this a little different. So what we're going to do here is we're going to cut the radius in half, so 0.5. Now, a lot of people make the mistake of leaving the radius out. What happens here is you want to make sure it's in the parentheses because you're actually cubing half the radius. So what happens here is we're going to end up getting 4 pi 4 times 4 times, or 0.5 times 0.5 times 0.5. We're actually going to end up getting 0.125. If you don't believe me, you can grab a calculator. 0.5, oops, clear this out. 0.5 times 0.5 times 0.5 again. 0.125, and that's just because I knew 5 times 5 times 5 is 125, because 5 times 5 is 25, times 5 again is 125. Because we had 3 numbers behind the decimal, we're going to have 3 numbers behind the decimal here. We're going to do this. All of this is getting divided by 3. Not quite sure why they wanted us to do a v prime, but here we are. And this is going to end up being equals, oh, I forgot. We're still supposed to have the r cubed because we're still going to have that r cubed. The only difference is the coefficient changed. So this is different than this because this one, we're plugging in half the radius. So when I do this, 0.5, I believe 4 times 0.125 is going to be 0.5. So if I do this, you get 0.5, oh shoot, 4 times 0.125, we end up getting 0.5. So when we write this again, we're going to have another fraction where it's going to be 0.5 pi r. We're going to cube this, and it's all going to be divided by 3. So if we look at this compared to our regular v, not our v prime, let me copy this. We see that there's a huge difference because that 4 is now a 0.5. So even though we only cut our radius in half, it's actually going to be, let's see how many times smaller it's going to be. So we always do new over old. So 0.5 divided by 4, it's going to be an eighth bigger. And I guess you could have seen that by this formula right here. So let me plug this in. We're going to say that cutting the radius in half makes the volume 8 times smaller. And just to kind of show you guys, instead of just you guys believing me that 0.8 or First of all, just to prove it, 1 divided by 8 is 0.125. Think of it logically. Another way of thinking about it, instead of doing it with decimals, because decimals do make it a little more complicated, 1/2 times 1/2 times 1/2, or since we already know how to use exponents, 1 cubed, 2 cubed, this is equal to 1/8. So I should have done that instead of using the decimals. It honestly probably made it a little more complicated doing it with decimals, but you can see why it's 1/8. Cutting it in half makes it, after we cube it, makes it 1/8 bigger. So what we're gonna do here, and we could have said it equal to each other. I personally just like comparing it to the original formula. If the volume of a full sphere is this, what is the volume of a hemisphere called? Half of a sphere. So in other words, we're going to take this volume and divide it by 2. Well, what happens here is you can essentially say that all of this is on the top. And if you, oh, shoot, it's supposed to be over 3. All of this is on the top, and then we're going to divide that by 2. Well, that's the same thing as doing this, as multiplying it by 1/2. We're going to do this and multiply it by 1/2. So that ends up being divided by 6. What is the volume of a hemisphere? So you're going to end up, you can write it like this. I recommend using the equation editor to do it. It's not as complicated as it looks. What you do is you do this, and on this, you're going to do a fraction again. So you're kind of doing a type of inception with these fractions. 5, 4 pi r cubed. This is a 3. This is a 2. This is equal to, I'm just going to copy these first two, or I guess I'll copy the whole thing, but I'll delete the 1/2. Where's the multiplication sign? Let me erase this. Over 2. And oops, forgot the equal sign. Actually, you know what I'm going to do? I'm just going to paste that same thing. Boop, boop, done. All right. And there you can see oh, they changed it to 2/3. That makes sense because you can reduce the 4 and the 6. I'm going to give myself a 4. I forgot to reduce some values, and I should have used fractions to make it more clear. All right, so that's pretty much that. Let's see what our next shape. Okay, we need to find the volume of this sphere. So we're going to do 4/3 pi 3 cubed. So this becomes 3 times 3 is 9, times 3 again is 27, because 9 times 3 is 27. So we have 27 divided by 3 times 4 pi. So we end up getting 9 times 4 pi, which means we get 36 pi. And that's what I usually recommend. If you can divide one of your factors, because these two multiplied together is a product, so them individually is a factor. If you can divide one of the factors by your denominator, go ahead and do that. It just makes your life so much easier by doing that. All right, so let's get on to the next question. So scaled values. So this is the idea of you multiplying it by something to make it smaller. We've actually kind of been doing this before. We just haven't really called it anything. A scale factor is we're doubling everything by 2. So for example, um, the scale factor, if we're doubling everything by 2, would be 8. Um, we're just going to say that the scale factor is cubed in this case because we're doing it to 3 different dimensions. And that makes sense because we're in 3D space. So let's work on these problems. All right, so let's take a look. We're gonna go here for our first question. Let me close out some of these. Not sure where that Khan Academy video came from when that tab opened. All right, so we have this cylinder. We want a radius and a height. I'm just gonna go with whatever was there. Oh my gosh, I can barely see that. Is that 12? It's a 12. I don't know why I decided to put yellow there. 12, the height was 14. My volume ends up being 6333.5. 6333.45. All right, then we're going to scale this by a factor of k. So let me read this again, see what it's trying to say. Create. Oh, okay. So, so create the smallest cylinder possible with the tool. Okay, so right off the bat, I should have read the directions. We're going to create this as small as possible. And the smallest one we can make, it looks like is 6 and 2. So, oops, 2. Oh my gosh. 6. Let's see what the volume is. 74. Oh, that's a lot nicer to do. 74.4. Now it wants us to scale factor. So everything is going to be doubled. So this makes this 6. This makes this 12. And as you can guess, what's going to happen here is our volume factor is going to be 8 times bigger. So you're just going to do this for all of them. So our scale factor for our original is going to be, oops, sorry, I multiplied this by 3. I was supposed to multiply it by 2, 4. This one I'm multiplying by 3, so this is 6. I think I got ahead of myself. This one is going to end up being 18. This one we're multiplying by 4, so this is 8. 6 times 4 is 24. And what's happening here is we're essentially just cubing this. I'm not sure why they're doing this. They literally just explained to us how it works. Because we're in 3 dimensions, of course we're just going to cube the k. And that's how many times bigger this is going to be. So we're going to notice that whatever this is divided by the original volume, we're going to get this number. So this new volume divided by the original volume will be our scaled factor. The standard formula of a cylinder is this. The scale potential, that is volume times that. Use algebra skills to derive the steps lead from that to that scale volume. Show your work. So what we're going to do here, first, we're going to write our initial volume. So volume equals pi r squared times height, but when we prime this, what we're going to do here, so this is the part I don't like. They want you to do it as a separate formula, and to me that just doesn't make any sense. We're just going to compare them. So if I do this, what am I doing here? I'm going to change everything by a factor of k. So pi is a constant, so we're not really changing that number. But in these parentheses for the r, for the squared, what we're squaring, we're going to have this kr, right? And then that's going to be multiplied by kh on the outside. So this ends up being, oops, equal to, where is it? Pi k control up 2, r control up 2, kh, which is in turn, we're going to see that we have 3k, so this ends up being k cubed pi r squared h. This is k cubed bigger than v. Oh, these were supposed to be v primes. Oh, sorry. This bottom one was supposed to be a v prime. Again, this should be apparent because if we're changing the sides of the dimension, what's happening is since we're in 3D space, this is going to be done for all of them. So in this next one, we're going to do it with a cone. And we're going to do the exact same thing for all of these. So I'm not going to go through how to type these in. You should know how to do it. You're going to make the smallest cone, or smallest cone possible. To do the work for this, we're going to do the exact same thing I did before. We're going to do v equals pi r squared h over 3 this time. And we're going to compare that to v prime, which is going to be, let me change the color, just make it stand out more. V prime, which is going to be pi k kr squared h over 3. And it ends up being the exact same steps because we're going to end up getting pi k squared r squared hk or kh, however you want to do it. And this is going to end up being k cubed pi r squared h over 3, and ends up being bigger. The next one, we're going to do it, but this time we're doing it with the volume of a pyramid. So if we look at the volume of a pyramid, we have this volume equals LWH over 3. So this V prime will be written as 3 KL times KW times KH all over 3. And this will end up being K cubed LWH over 3, which again is K cubed bigger. So this, I feel like it just kind of makes sense. There's 3 dimensions. You're going to see it 3 times. If we did this with even if we did this with a sphere, it would be the same thing because a sphere is 4/3 pi r cubed. So if we do the k r cubed, this is why we didn't do this in this exercise because we technically did this in the last exercise. So I felt I got a 5 on this, but you might feel a little differently. If you need help with any of these, again, feel free to comment and maybe someone else can reply if I don't have time to get to it, but I usually try to get to all my comments as soon as possible. All right. moving on here. So we're going to change everything by a factor of 5. So because we're in 3D space, if every dimension is changed by a factor of 5, we're actually going to multiply this out by 125. It's going to be 125 times bigger. So we're going to get this 64, multiply it by 125 bigger. So it's 8,000. So just making every dimension 5 times bigger makes the volume like way bigger, 125 times bigger to be exact. All right. So moving on to summary, buildings and everything have all kinds of volume and they can be affected in different ways, especially in three-dimensional space. It's not as simple as to double something, you just double one of the sides. You have to do, or actually it is that simple. I was gonna say, I'm like, if you wanted to double volume, you don't double every side. You only need to double one of them, assuming that you don't have any um, exponents or anything changing it. Because obviously, if you double the radius, you end up making it 8 times bigger, which is not something you really want to do. Um, So yeah, that's pretty much it on how to use formulas. I know this one was an awkward one. I almost feel like they could have combined some of the material with the other one, but there are some things in there that were a little harder to grasp. As always, make sure when you're working on this to really understand the material and really reflect on it and take your guided notes. Uh, like finish your guided notes to help you out with it. All right, guys, see you in the next video.